Hi, my name is Rory Solomon, and my contribution to the Proximity Project is a discussion of the concept of network proximity and how that helps us understand the changing nature of proximity in the 21st century. In one sense, this entire project, the entire Proximity Project, is about proximity and networks. But by focusing on the concept that we're calling network proximity, I'll be drawing attention to the ways that proximity is produced by the physical apparatus of networks, the material infrastructures of communication. I'll show that while digital networks produce new immaterial geographies, they are themselves already geographical objects in the traditional sense. And even as they produce new forms of proximity, they also leverage distance and sometimes even produce it in new forms. So I'll start with an anecdote. This is a story that was first posted to an email forum for system administrators in 2002 and was widely circulated since then. In the story, a sysadmin recounts that they were responsible for a university email system in the mid-1990s when they received a tech support request from the chair of the statistics department, who claimed that no one in the office could send emails farther than 500 miles. The department chair had even called a geography-focused statistician who had created a map that seems to prove this limitation. Of course, the sysadmin was perplexed because, as we all know, that's not how email is supposed to work. We all know that email messages are made up of data, digital information, which we typically think of as virtual or immaterial. And when we send data like emails, we expect that the process shouldn't be limited by properties like physical size, weight, or distance. So what was going on here? Well, it turns out that the server had been misconfigured and a timeout had been set to 0 seconds, meaning that if the server didn't get a confirmation of receipt from the recipient's email server within 0 seconds, it would cancel the message. Now, computers, of course, process data very quickly, but not instantaneously. And on this particular computer, 0 seconds actually translated to about 3 milliseconds. The sysadmin then realized that due to the network configuration on campus, the email limitation was due to how far data could travel along a wire in that much time. Digital information, of course, moves by electrical signals, and the speed of electrons is determined by the speed of light. So with a quick calculation, this person determined that in 3 milliseconds, electrons could travel about 558 miles, thus explaining the strange problem and then, of course, reconfiguring the server. I start with this example because it illustrates several things. For one, it touches on some of the operating principles of digital networks like routing, which I'll talk about later. But it also illustrates that digital networks are physical things with materiality and geography. And this is the main idea that I want to impress upon you today: the ongoing relevance of materiality and physicality in the study of geography and digital networks. Even as digital networks invite us to think about new forms of culture and cyber-social relations, of instantaneous connections that span the globe, the concept of network proximity emphasizes that these connections are always forged by material circumstances, things like physical infrastructure, labor, political negotiation, and capital investment. And while these things yield new, seemingly immaterial geographies, they are still also already physical, geographical objects in the traditional sense. To better understand this, let's take a step back and make sure we have a deep understanding of networks themselves. I'm sure that many of us at this point have an intuitive idea of what this term means, but let's take a closer look to develop a more precise and technical definition. In a testimony to how important networks are to so many domains of modern life, the Oxford Dictionary offers us dozens of definitions of the term and its variations. It gives us the term as an adjective, as a modifier in phrases like network effect or network culture. It also defines the term as a verb, as in to network, meaning to connect something. Focusing on the senses of the term as a noun, we see that OED gives us a handful of different definitions here, talking about fabric and chemistry. But for the purposes of the Proximity Project, the definition that I want to focus on is the one here, circled here, quote, any net-like system of interrelated things, such as topographical features, lines of transportation, or telecommunications routes. Related to this definition are a handful of specific contexts. OED lists cables for the distribution of electricity, a broadcasting system of linked transmitters. This is the sense of the term as in like a television network. And of course, a system of interconnected computers. Drilling into this definition, we see some notable and exemplary usages. As early as 1839, we see the term used to describe a network of islands Other usages are a network of railroad, a network of waters, a network of trenches, a telephone network. Discovery Magazine in 1937 wrote of the network of airlines. Lewis Mumford, in his History of Urbanism, describes a network of alleys and streets. And for any science fiction fans, in 1974, Ursula K. Le Guin wrote of communities connected by communication and transportation networks. My point in highlighting these examples is to show that networks have always been about geography. So even as we think about communication networks affecting proximity in new ways, we should keep in mind that notions of distance are kind of baked into networks and what they do. For the purposes of the proximity project, I'd like to offer a slightly different definition of what we might call the network concept. And we can define that as a technique for formally describing some pattern of circulation, which implies several components. First of all, locations, meaning a collection of points or destinations, like the to and from points. Also moving things, meaning the objects, people, or messages that move or attempt to move between these locations. These can also be flows, like water, electricity, or data. And lastly, the connections, meaning the ways that these points are linked, the various paths that the moving things can take between locations, which can be wires, roads, waterways, veins and arteries, or something else. Once you start looking for networks, you can see them almost everywhere. Here's a transportation network where the connections are roads and the moving things are independent vehicles. We also can model transportation networks of rail. Here's a urban subway system. Air travel can also be understood as a network. Here we have a map from 1987 of what's called a hub and spoke model for one airline. It's called that because this airline doesn't offer flights between every city, obviously, but instead relies on a small number of centralized points called hubs. If you wanted to fly between two hubs, like say Seattle and Minneapolis, you could probably easily do so directly. But if you wanted to fly between smaller destinations, like say Reno and Wichita, you'd probably have to make a stopover, in this case, being routed between Los Angeles and Memphis. Networks can also be biological. We could think about the human body's cardiovascular system as a network of organs connected by veins and arteries that circulates blood between them. And of course, as we've heard about so much recently with the COVID pandemic, networks are also used to model and understand the ways that viruses circulate from person to person for the purposes of contact tracing and epidemiology. To take an example of a communication network, here's a map of AT&T's long distance lines from 1898. The lines on this map represent actual copper wire that had been run from each of these cities. And if you wanted to make a phone call at this time outside of your local city or town, the audio signal would be transmitted along one of these physical wires through intermediate hubs. For example, from Tallahassee to Montgomery, you'd probably have to be routed through Atlanta. Originally, this process of determining intermediate points for phone calls was done by human operators located at switchboards in these cities. And eventually this process was automated by electromechanical and then digital machines. Of course, interconnected digital devices is one of the most predominant examples of the network form today. This shows a small number of computers connected on a LAN or a local area network. And this shows the connections of millions of computers, visualizing how digital data flows globally along the pathways between major cities. The connections here are mostly fiber optic cables, mostly laid along the ocean floor. And for more information on this topic, you can check out Nicole Staroselsky's 2015 book, The Undersea Network. This example illustrates how networks, even digital networks, are geographical objects, but also that when digital communications emerged, it already had a rich history of earlier network concepts to borrow from. This geographic aspect of networks is such a potent concept that when the internet was in its infancy, the language of geography offered some of the most useful terminology for people to talk about and explain these new systems. And the clearest example of this was the proliferation of highway metaphors used to describe the internet in its early days in the 1990s. So for example, here's a representative sampling of this terminology. The New York Times in 1993 wrote of an electronic superhighway. Here's a 1994 explainer for children featuring Al Gore that talks about the information superhighway. 1995, Connecticut newspaper talks about a data highway. Here's discussion in 1996 about fiber optics making the info superhighway speedier, again, using velocity as a metaphor. Here's a cautionary note in 1999 that the information superhighway might have potholes. And lastly, here's a guide in the New York Times for new users called on-ramps to the information superhighway in the year 2000. And I would like to just offer as an open question here that perhaps this proliferation of geographical terminology to speak about networks metaphorically could have actually impeded our ability to understand that networks are also geographical in a literal sense. But I'll leave this as an open question. Throughout the latter part of the 20th century, the network form became so prevalent in all areas of society that many studies emerged focusing on how networks shape society and culture. And here's just a small sampling of those texts. Taken together, these define a kind of network epistemology, meaning a way that networks came to shape how we think and how we form knowledge. And one key tool of this network epistemology is the network diagram. Network diagrams are the visual form that we most typically use for representing networked configurations. And the analysis of network diagrams is so important that it has its own branch of mathematics and computer science called graph theory. In the technical jargon of this field, network diagrams are referred to as graphs, and the locations are referred to as nodes, typically represented by small dots, and the connections are referred to as edges, represented by lines. Nearly all the examples I shared earlier have a very clear presence of this type of visual rhetoric, which you can see here. And network diagrams can be either directed or undirected. In a directed graph, the edges are indicated by lines that have become arrows, while an undirected graph might represent a set of roads where each goes in both directions, but a directed graph would be used to represent, for example, a collection of one-way streets, or maybe a system of rivers, or maybe even a conceptual network like the evolution of species, products, or ideas. And to take examples that most of us are familiar with here at the bottom, we could think about the connections of Facebook as an undirected graph, since friendship in Facebook is always mutual, while platforms like Twitter, Instagram, and TikTok would be better modeled as a directed graph, since one user can follow another without that being reciprocated. Another type of network diagram is called the weighted graph. In this type, a weight is associated with each edge, and these weights can represent some sort of cost, for example, geographical distance, or perhaps the time, money, bandwidth, or energy usage needed to traverse that particular connection. Adding weights to a graph can make the process of finding routes much more complicated. For example, if we were trying to, if a person or message was trying to move between points A and B, routing might determine that going through node C here would be more efficient, since the total cost of that route is 7 as opposed to 8 if we went directly, using the example of these arbitrary abstract weights in this example. Thinking about weighted network diagrams brings us back to my main point, which is that in any study of networks, even digital networks and so-called cyberspace, we shouldn't ever forget to keep in mind the physical material realities of these digital circulations. And we can describe this relationship between abstract diagrams on the one hand and physical infrastructures on the other as a relationship between topology and topography. In her analysis of fiber optic cables that I mentioned, Staroselsky addresses this when she writes that, quote, "To understand the routing of digital networks, we need to move away from network topology, the analysis of the mathematical structure of connections, and towards topography, the analysis of how these connections have been embedded into historical and geographical matrices." While this is a text within the field of media studies, geographer David Harvey seems to be grappling with a similar question from this different field. Harvey writes that geographical knowledge is always site-specific, and he considers the challenges involved in trying to generalize this type of knowledge into abstract ideas. So this is kind of a dual or inverse question from these two fields. Emphasizing materiality prioritizes topography over topology, drawing attention away from purely abstract models and diagrams and towards the ways that these networks are situated, embedded, and located within specific histories, cultural contexts, natural environments, and physical terrains. Pictured here on the right is a photograph from Staroselsky's book of 2 undersea fiber optic cables coming ashore in Guam. Network engineers often speak about the long haul versus the last mile. The term long haul refers to the long wires that connect major hubs that form the backbone of networks like the internet. On the other hand, the last mile is the part of the network that connects individual users. For example, the wire coming into your house off the street. One thing to keep in mind is that all networks are local in the sense that the last mile is always local. Even though you might be accessing data from across the world, it ultimately passes through local connections before it reaches you, which means negotiating local laws, ordinances, and relationships with your community and neighbors. Staroselsky describes how this relationship is always relative. One person's backhaul might be another person's last mile. For example, when undersea cables connect major cities, come ashore on Pacific islands or in small coastal communities, a phenomenon that she calls surfacing. Sometimes these questions of legal jurisdiction can pose real problems to the material mechanisms that construct network proximity. One example of this comes as a complication for routing. So I've already mentioned some examples of routing, like determining flight stopovers and determining the pathways of long distance telephone calls. Since the days of phone operators manually routing calls, we've developed many routing algorithms for automating this process, and a wide array of different routing algorithms exist for different contexts. And this is a rich area of research in computer science. Paul Durish's article, Protocols, Packets, and Proximity, goes into excellent detail about this area of computer science. But as I mentioned, sometimes this purely rational or automated approach is insufficient. Sometimes just considering path weights or number of hops is not enough to solve a routing problem, and we have to take into account other topographical features like environmental costs or historical narratives. One example of this comes from the early days of the COVID pandemic lockdown, when nearly all office work had moved to online platforms. During this time, concern emerged among US companies that Zoom had routed the data for video meetings through Chinese data centers, sparking a lot of xenophobic fear of eavesdropping by geopolitical competitors. Zoom had to admit that it had done this and issued an apology, but then it quickly pivoted and monetized the problem by giving its paid customers the option to specify that they did not want their data routed through Chinese servers, turning the geography of data flows into a premium networking service. This example illustrates how routing can be a deeply political process, and how even though we don't typically think about how our data moves from place to place, there are times when these determinations can be recast as a commodity. I'll end with two examples that show the importance of geography to network proximity, and that help us think about how network proximity continues to change in the 21st century. The first is about data centers and real estate. In 2010, Google bought a huge building in New York City for $1.9 billion. Part of it, of course, was used for office space, but a large portion of the building was to be used as a so-called telecom carrier hotel. Rooms full of servers and networking equipment used for interconnecting the physical wires from networks around the world. Google is not alone in locating telco hotels in New York City. In the book Networks of New York, Ingrid Burrington mapped the location of many key data centers and telco hotels throughout the city. And I share this to provoke the question about of why companies would do this. Why would they choose some of the most expensive real estate in the world as a place to house computers and digital data that could theoretically be located anywhere on the internet? A 2020 report from MIT Tech Review explains that there are advantages to placing data centers in urban areas because data centers are such energy intensive activities that urban areas have the kind of established infrastructure needed to easily support them. But it's not just a question of physical infrastructure. A similar report from McKinsey explains that many companies are choosing to place data centers in expensive urban areas to be closer to customers. Telco hotels require highly skilled labor, often face-to-face, and often from people who simply want to live and work in areas with high concentrations of other skilled workers, not to mention the exciting enclaves of social and cultural activity. So big cities still remain important locations, even in cyberspace. And as much as real estate costs demonstrate the value of place in our networked society, the fact that these real estate costs are apparently cheaper than the alternative shows how incredibly costly, if not impossible, it would be to build out all the other material and social infrastructures at these alternative sites. As a last example, I want to consider the routing of data for one very specific type of digital network activity, high frequency trading. So high frequency trading, or HFT, is an area within the finance industry that buys and sells stocks for very tiny gain, sometimes even for a fraction of a cent. But it does this at a massive scale, sometimes making millions of trades at a time. Being able to do this requires the ability to get market information and to execute trades faster than competitors. Sometimes the competitive advantage is only milliseconds faster. At these speeds, even fiber optic cable isn't fast enough. And trading companies have developed high-speed transmission protocols to send data wirelessly using shortwave and microwave radio signals. This can lead to intensely competitive capital investment projects, a kind of infrastructural arms race, where rival firms compete by building slightly closer and closer antenna. One example of this is unfolding now in Aurora, Illinois, which holds the data center for a large Chicago-based stock exchange. That data center is pictured here in the white building on the left. Two major firms are presently competing to build antenna towers, but one would potentially block the other. And this issue is being adjudicated at the level of local government. One city council member who's voting on the issue stated, "I came from being a guy who didn't know where the cloud was to realizing that speed matters, even just being a millisecond faster." Obviously, this evokes the anecdote that I started this talk with, and it also drives home the point that massive capital investment is needed to produce the appearance of seemingly ubiquitous instantaneity in cyberspace. To conclude, a sign along the highway near Barstow, California declares, quote, "absolutely nothing for the next 22 miles. And I think the humor here is twofold. We might initially be amused about the sheer lack of stuff along the road, a kind of paucity of topology. There are no nodes along this stretch of network connection, no gas stations, towns, no snacks, or even charismatic scenic overlooks. But the comedy also comes from the fallacy of this declaration, the wrongness of a kind of topological chauvinism, because in fact, of course, there very much is something along this route. We see telephone poles with wire. We can assume the plants and animals of the natural environment, not to mention the minerals, the soil and dirt, and of course, the road itself, or so the driver hopes, if they're going to reach their destination. And hopefully the asphalt is relatively smooth and recently visited by maintenance workers if the ride is to be comfortable. Of course, the sign, what I'm calling the topological element here, isn't useless. It signals important information to the traveler, like the cost of this particular network linkage measured in miles and perhaps also gallons. And so in order to navigate this linkage, in order to make it to the next node, the traveler must pay careful attention to these physical conditions or ignore that material geography at their peril. Thank you.